This section 10.8 is on vectors, and we'll define first what a vector is. So actually, maybe I will introduce vectors using an example. So let's say you have the wind that's blowing somewhere. So you're here and the wind is blowing. Let's say this is north, this is east. Wind is blowing northeast, so it's blowing like this. So with the compared to the east, it's blowing at an angle of 45 degrees. And let's say it's blowing at a speed of 15 kilometers per hour. Okay, so the wind is both defined by its speed and by its direction. Okay, and you can indicate that those two quantities using an arrow like this. So the arrow, the length of the arrow is somehow the magnitude of this quantity. So here 15 kilometers per hour, and its orientation is also linked to probably some angle that it would make with some reference line, and that would describe its orientation or direction. So a vector is essentially going to be represented with an arrow, and it's basically going to be a quantity that has a direction and a magnitude. So we'll write that down. So a quantity with a direction and a magnitude, okay, is a vector. Okay, they are represented using arrows. And we'll see, sometimes we're going to represent them using coordinates. Okay, so here my example is wind blowing at 15 kilometers northeast. Now, how do we represent this arrow using coordinates? Now imagine that this is where you are, and to make this convenient, assume you're at the origin of the Cartesian plane. Okay. Now, imagine this is the wind here blowing at an angle of 45 degrees with a magnitude of 15. Okay. So the tip of the arrow, which is called the head, would be located on some circle. Like this. It would be on some circle of radius 15. And the wind is making essentially an angle of 45 degrees with the x-axis, because the positive x-axis is pointing in the direction of the east. What would be the coordinates of this point? Well, if it's a unit circle, the coordinates would be cos of 45, sine of 45. But right here, this circle has been magnified by a factor of 15, which is the value of the radius. Like, it's 15 times bigger, so every coordinate is 15 times bigger as well. So the coordinates of the head of our vector are 15 cos 45, 15 sine 45. In other words, here there would be 15 root 2 over 2, 15 root 2 over 2, and if I evaluate this approximately, I get 10.61, 10.61 approximately. So this is how we can describe a vector using coordinates. But it needs to start at the origin. So this is called the head of the vector, and this is called the tail of the vector. So we could basically say that the coordinates of a vector are the coordinates of the head of the vector if its tail is at the origin. Head of the vector if its tail is at the origin. But when the wind is blowing, okay, northeast at 15 kilometers per hour, okay, all around you it's blowing in that direction, okay, and it's essentially the same vector that describes the wind anywhere around you. So it doesn't need to be placed at or start at a specific point. It's the same vector throughout, okay. So this is one thing that's particular about vectors. Independently of where they're placed in the plane, it's the exact same vector. So this vector here, okay, well, maybe let's start with the one we just described that starts at the origin, okay, with coordinates 10, 61, 10.61, 10.61, okay, it's the same as this vector that sits here, that starts maybe elsewhere, but it would still have the coordinates 10.51, 10.51. Okay, so when you see those coordinates, you can't assume that this is where the head is going to end up. Okay, it will be the head if the coordinate starts at the origin, but otherwise, if it starts elsewhere, it could still be defined by those coordinates even though it doesn't start at the same place. Okay, so let's add this. So vectors are the same in this diagram. Independently of where their tail is. Okay, or I should say where they are positioned. Okay. So when the tail is actually at the origin, we say the book says it's a vector in standard position, and then its coordinates are exactly the same as the coordinates of the head of the vector. They'll also say a position vector. That's okay. They'll say a vector in standard position or a position vector. Okay. So there's this duality point vector. So if you've got a point in space like this, let's say 3, 2, you could associate a vector to it that starts at the origin and that ends at 3, 2, and it would have the same coordinates, 3, 2. So that's why you say it's a position vector. It's a vector that sort of points to a point to locate it. Okay, so you could have like a whole bunch of position vectors like that, but they all start at the origin. Now we're gonna find the coordinates of a vector when the tail is not at the origin. Is not at the origin. Because when the tail is, you just take the coordinates of the head, and those are the coordinates of your vector. But what happens if the tail is not located at the origin? So imagine that I have a point A. So often it's going to be the case we're going to label points with capital letters. So coordinates x1, y1, and this is, let's say, point B with coordinates x2, y2. Okay. What would be now the coordinates of this vector? Okay. So in other words, this vector would be would be placed here, right? If I make it start at the origin. Well, somehow it'd be parallel. So it'd be more like that, right? So I'd like to know the coordinates of the head if the tail starts at the origin. So how do I do this? Well, take a look at this triangle here. Okay, this right triangle. If I look at this leg of the triangle, this is x2 minus x1. It's the difference in the x coordinates of the points. And this is y2 minus y1. So we go forward by x2 minus y1, we go up by y2 minus y1. So this will end up being the coordinates of our vector that starts at the origin. So the coordinates we're looking for are x2 minus x1, y2 minus y2 minus y1. Like that. So maybe we can write that with a formula. So the vector AB, so sometimes we write it like that too. So this is the vector starting at A, ending at B, okay, is equal to the vector with coordinates x2 minus x1, y2 minus y1. So that's kind of like a little formula. To remember. So let's take a look at an example with some numbers. And on purpose, I've actually created a vector that's going downwards. So I've got A here with coordinates 1, 4, and B with coordinates 3, 2. Like that. And this is the vector. Okay. So of course it's associated to this position vector, and what we're going to try to find are the coordinates of the head of the position vector. So the vector AB, according to the formula, it's x2 minus x1, b2, y2 minus y1. So of course here the y coordinate of our position vector is going to be negative. Okay, and that makes sense because here we actually go forward by 2, but we go down by 2. Okay, so this is why we have a negative 2. So this is why this point ends up being 2 minus 2, and those are the coordinates of our position vector. And those are also the coordinates of the vector AB, because once again, vectors can be placed anywhere we want in the plane. So the two vectors in yellow are identical. We're going to talk about the magnitude and the angle of a vector. And in particular, how do we find the magnitude and the angle if we have the coordinates of the vector? So let's say we've got a vector making an angle theta with the x-axis, and its coordinates, this is a position vector, are AB. What I'd like to know is the magnitude here. What's the magnitude? It's the length of this vector, or in other words, it's really the distance from the origin of point AB. And we've sort of seen this already, but it's very easy to obtain. So if this is vector AB, this leg here of the triangle would be A, this would be B. So the magnitude is the hypotenuse of the triangle, of this right triangle, and its value would be the square root of the sum of the squares of the legs. So this is a formula for the magnitude. How do we find the angle? We could say that tan of theta is b over a. So theta is going to be the arctan of b over a. And I can tell you this formula is going to work even if you've got positive or negative values of b. But of course, it's going to give you an angle, okay, you have to be careful here. This angle is going to be between minus pi over 2, because it's the arctan, minus pi over 2 to pi over 2. So you might have to adapt this. So it's going to be linked to the arctan, but you'll have to adapt it, because if the angle you're looking for is not in that range, or if you want an angle that's positive, you'll have to find a you'll have to find an angle theta using this this formula. So it's arctan on this figure, but we might have to adapt the formula in other cases. So we will look at that in another in an example that's coming up. So let's return to the magnitude. Okay, so the magnitude is written. So if this is, let's say, vector v, okay, the magnitude would be, in your book they write it like that, okay, kind of like absolute value symbols around v, so that stands for like the magnitude. The reason is that the absolute value of a number, it's kind of the magnitude of the number, so this is why we can use this symbol. But often with vectors, we have these double vertical bars just to specify that we're dealing with vectors. So you can use both. In the book they use the first notation, okay, which is like an absolute value symbol. I prefer the other one, okay, and the formula is, like as we said, the sum of the squares of the coordinates of the vector. What I'd like to know also is, how is the magnitude defined in terms of how the coordinates are defined in terms of the magnitude and the angle. So if I've got a vector like this making an angle with the x-axis like that, with a magnitude of we call this the norm of v. So with a magnitude norm of v, how do we find the coordinates? Well, you have to imagine that the head of the vectors is on a circle with a radius norm of v. So the coordinates are, well, if it would be a unit circle, it would be cos theta, sine theta, but everything's been magnified by a factor of norm of v, or by the magnitude of the vector. So those would be the coordinates. In other words, this side here, this is norm of v sine of theta, and this side here is norm of v cos of theta. So we'll look at some examples. So imagine I've got an angle making an angle of a vector making an angle of pi over 3 with a magnitude of 5. What would be the coordinates here? So I'm looking for the coordinates. Well, the coordinates are simply, so let's call this vector v here. So v would be the vector with coordinates 5 cos of pi over 3, 5 sine of pi over 3. Okay, and I can evaluate those. This is 5 cos of pi over 3 is a half. Sine of pi over 3 is root 2 over 2. Okay, and those would give me the coordinates. Let's look at another example, and here I'm going to try to find the angle, and on purpose I've chosen an angle that's not an acute angle. So I've got a vector, I'm given the coordinates, okay, and let's say this is vector v, so we can just write v equals this. Okay, so what's the magnitude? Well, the magnitude would be the square root of minus 3 squared plus 2 squared, because really it's kind of like the distance from the point, minus 3, 2, to the origin. So so it would be square root of 9 plus 4, so square root of 13. And what's the, let's say this is the angle, okay? What's theta here? Well, if I look at this triangle, okay, the supplementary angle to theta is phi, okay, or in other words, this is just simply pi minus theta. And the sides or the legs of the triangles are what? There are 3 and 2. So the angle pi minus theta, its tangent, okay, is 2/3. Okay, so that means what? It means that theta, and this is an acute angle. So on purpose here, I've got an acute angle. So I'm going to get, by taking the arctan, the value of that angle. Because it's acute, the arctan gives me an angle between minus pi/2 and pi/2. So if it's an acute angle, I'm going to get exactly what that angle is. And the arctan is here 33.69 degrees. Okay, so in other words, yeah, so I've got this angle here, which is 33.69. So theta, of course, is 100. Well, maybe I should work in degrees here, because everything's in degrees. And or I could have worked with radians here. Okay, it would have worked well, but because I'm working in degrees, I'm going to put 180 degrees. So theta is going to be 180 degrees. Okay, so a full rotation minus the 33.69 degrees. But essentially you get this, right? If you solve this equation for theta, this is exactly what you get. So so in this case we get 56. Sorry about that, well, not 56, but 146, sorry, 0.31 degrees. So that's why I was telling you, you can only use arctan of the ratio of the coordinates if you're working with an acute angle that's positive. Otherwise, you'll have to adapt your answer a little bit. Okay, so draw a diagram, and it's really going to help.